Right, welcome to the second lab. This is the Scour lab. Before we get to the actual lab, let's just have a look at the process of Scour. We've talked about it in the lectures already, so this is a bit of a reminder. So, the first thing we've got here is a cylindrical structure which is embedded in a mobile bed, and it might be embedded to a depth where it reaches the bedrock. Now this could be a bridge pier or offshore wind turbine, let's say. So what happens when a flow approaches this structure with our loose mobile bed around it? So let's draw our flow. It's approaching. With this cylinder, we know that that flow is going to reduce to zero once it hits this structure here. Okay, so the actual flow velocity becomes zero. So thinking about that in terms of pressure, it's a low pressure, high velocity. The pressure is beginning to increase as we approach the structure, and thereby the velocity must decrease. Okay. Once it decreases, you get a little bit of a roll here of the flow, a bit like the bow wave of a boat. But a lot of that flow then is forced downwards towards the bed. Okay. Of course, it's got nowhere else to go. It can only go down. It increases in velocity as it approaches the bed, and when it hits this bed, this is a bed which is made of sand. It's a mobile bed. It can be moved if the velocity increases. And so we get then the development of a scour hull. So a hole starts to develop around our structure. You'll also get the boundary layer around the side of the structure as some of the flow is pushed around the side here. And let's draw it like this. When we're thinking about what happens to the flow around a cylinder, let's have a look at the top down, and then we can focus on this. So if you recall, our flow approaches our cylinder. It reduces to zero velocity maximum pressure, and then it's deflected around our cylinder, and so the velocity starts to increase. And with that, the pressure must decrease. The velocity increases. The pressure becomes lower and lower and lower. As it gets around the side of the structure, and the reason, of course, the velocity is increasing is because of continuity, Q equals U times A. The shape of this structure is decreasing the area that the flow has to travel in. So as we approach the rear, the shape of our structure is falling away, and our area is increasing, so our velocity doesn't have to be as high in order to retain continuity. And so what happens? The velocity starts to decrease, the pressure will increase to the point that the pressure is so high, and there's so much water coming behind it, that it's no longer, the boundary layer is no longer able to stay attached to the structure. And it detaches like this. And you get the formation of these counter-rotating coupled vortices. And so that's what's happening behind our structure. We're getting these large counter-rotating vortex formations. And there'll be one on the other side as well. Over time, one will form on one side, one will form on the other side, and they'll slowly peel off downstream. Now, these are rotating like this, so they're actually sucking the water up. It's a little bit like a mini tornado. And therefore, with this mobile bed, you get some of the bed sucked up, and all this sediment transport here is transported into this wake, and therefore taken downstream. And these two things together develop our scour hull. The third thing, which is also very important, is the creation of a large horseshoe vortex around the base of our structure. So I should correct myself. These three phenomena is what's developing our scour hull. Now, what is the problem with that? Well, the problem with that as an engineer is you've designed something to be a safe structure, which is, I don't know, this one's holding a wind turbine, let's say. It's offshore. It's tens of millions of pounds to construct and take out there. And suddenly the waves and the tides are coming past this and developing a large scour hull. So your bending moment is going to increase because the lever arm length is increasing because of this scour hole. Any cables which are attached to it might be exposed when they're not designed to be exposed. It might change the vibration behavior of the whole structure if it's got a wind turbine on top, and etc. You might even induce vortex-induced vibrations of the whole structure as well. So it's a very important thing to be aware of. In the lab, we're going to look at that flow and that sediment transport around small structures which are analogues of bridge piers. The final thing that I should mention as well is when we think about scour, what are the different parameters that might affect it? And this would be what this equation is as well. So the depth of scour, the depth of this scour hole, have a think about what is controlling that. Going through this, it's a function of all of these different variables. Okay, U, which is the flow velocity, sure, that must be faster flow velocity, bigger scour hole. UC, which is the critical flow velocity for incipient sediment motion. So how fast does this flow need to be to start moving these rocks or whatever they are? That'll be to do with the weight of the rocks as well. Obviously G for gravity. The height of the water must have an effect. The depth of the water must have an effect. The diameter of the structure must have an effect. What we've got here, we've got the density of the fluid. So why would that be important? Well, it's because it's water in most cases, but seawater is more dense than freshwater. So if this is a freshwater bridge, it's going to be different than if it's a offshore wind turbine in the ocean, depending on which ocean it is as well. The density of the sediment, of course. This is the viscosity of the fluid, so how thick the fluid is. This is the angle of attack of the flow. So if the flow is coming straight on, that's one thing, but if it's coming side on, how much shear is there in the flow? Doesn't really matter for a circular structure. This is, I need to get my sheet. This is the shape of the structure, and this is the alignment of the structure, and G is, hold it, that is the lateral shear in the flow. Okay, it'll be better in the lecture for that. Right, so let's focus on this structure as the flow's approaching. Now you can see very clearly already there's significant scour hole has developed on the leading corners. You can probably only see this corner, but it's symmetrical, so it's the same on the other one. What you can see is the flow's approaching. Oh, and on cue, our little cylinder pops out. The reason it popped out is that you can see there's a large scour hole that's developed already. Ignore that one. Back to this square one, you can see the flow's approaching, and then it comes to the leading edge, the leading corner, and it will separate because it's such a sharp corner it can't stay attached, the boundary layer. And so as it separates, you can see there's a swirling of sediment along the corners. When you look very close, you can see that lateral vortex has formed. It's taking the sediment downstream, but at this point it loses a lot of that energy, and so the sediment comes out of suspension, and we get quite a lot of deposition on this side towards the rear of the structure. So there's a scour hole developing on this side, and it's still going, and there's deposition on that side. And so the loading profile from the sediment on the structure is changing. If you look very closely, you can see where the extent of the horseshoe vortex is at the front of the structure, because there's a little concentric circle. There's the outer bit of the scour hole, and inside there's a little circle there where you can see sediment in motion. And that's the horseshoe vortex, which is doing this around the base of the structure, picking up the sediment, taking it to the sides and carrying it downstream. Now our cylinder didn't last very long, but usually when you have a bridge pier it would be shaped rather like this, a streamlined shape. And you can see, compared to the bluff body, the rectangular shaped here, that the scour hole around this one is much less deep. There's less deposition on the side. And we design it like that because obviously this leading edge is a lot more streamlined, so there's less of a downflow is able to form on that than there would be on this width here. And the acceleration of the flow of the boundary layer around the structure is much slower because it's a more streamlined, a more gentle increase to its maximum width. Now its width is the same as this one, but it it allows the flow to move past it without having to accelerate too much. Okay, so that's the end of part 1. Right, so this is part 2, where before COVID times, I'd get you to design scour protection for a bridge. Now this one has got some stones around it, some armour stones, to try and reduce the amount of scour that occurs, and this pier here is left unprotected. So that's probably going to fail. There's a very big scour hole already. But why is this one doing better? Well, essentially the scour protection, and here we go, off it goes. Your school bus of kids going over at the time, they've all fallen into the river. It's a disaster. Your engineering firm's taken to court, etc., etc. But if you designed it like this, you've done a better job. So you know there's going to be some scour, and you know you have to do something about it. You have to protect the area around your structure. So why are these stones doing the good job? Well, if you look very closely, you can see there is scour developing around this structure. It's developing around the stones. So the flow is still separating off these surfaces, but the stones themselves are much heavier objects. So we often call this armour stone. And so the flow of water, the acceleration of the flow, is not going to be large enough to move these armour stones. And they therefore protect the bed underneath it. Now usually you would have something called a geomat underneath, which is like a special mat to protect the sand, and then you put the stones on top, for example. Or you would have a steel collar which would wrap around the entire structure. Other ways of doing this is you could put another pier in front of it, like a little sacrificial pier. Here's one I made earlier. So you could pop that in. And the point of that is that when the flow approaches, this pier sacrifices itself to that flow, as it were, by allowing scour to develop around it. But by the time it's done all that, it's bled a lot of energy. The flow is much slower when it approaches your pier of interest. So there are a variety of different ways of protecting piers from scour. The armour stone is most often used, especially in the offshore situation. So for example, an offshore wind turbine. So it's done very well here. I'm very pleased with that. And that's the end of part 2.